Hey class, so one of the things that finishing up the u substitution notes kind of leads students to believe is that you can take the antiderivative of anything. That if I just pick the right technique, I'm going to be able to do it. So, if we look at this antiderivative right here, or if we try to take the antiderivative of this, you could try letting u be like the x cubed plus 1, but then du would be a 3x squared. We don't have that. You might think that, well, let's do the Hart method, but the Hart method doesn't work upside down. If you had x cubed plus 1 over x, that would work. That thing you can do the Hart method for, but not vice versa. Because our goal here is to figure out what f of 3 is. So normally you would take the antiderivative, and you get something plus c. You could plug in your initial value and solve for c. And then once you know that, you can plug it in and find f of 3. But without having the antiderivative, you can't solve for c. So what do? We think about what the definition of the definite integral is. So what do? You take the antiderivative and you plug in your endpoint, your final, and then you plug in your initial and you subtract them. So this is written a little bit different than I would write it. I would say, okay, 0 to 3 of x over x cubed plus 1 dx. What this is the antiderivative, which I don't know, evaluated at 3, minus the antiderivative evaluated at 0. This is our final minus our initial. So how do we do that? Now, there's two ways of getting at this thing here. Number one, well, actually 3 ways. 2, 3. So number one, take the antiderivative. But we've already talked about how we can do that, so this is no good for this problem. 2, we can find the area under the curve, which is actually what we're going to do, but how do we do that? We could try doing our delta x and all our x sub I stuff, but then I've got to plug into this thing with x sub i's. Yeah, that doesn't look like it's doable. So the third thing is we're going to use our calculator to calculate the area under the curve. So it's not really a third thing, it's just that we personally can't find the area under the curve. That doesn't mean that the calculator can't shade it and tell you the height and multiply by a bunch of little widths. So the calculator's going to find it. Now, once we have this, we can solve for anything. Actually, I'm going to go a little bit more in general up here to the right here. So if we're looking at the integral of f of x from a to b, a would be our initial, b would be our final, dx. And so we're going to say that this is f, capital F, which is our antiderivative, of b minus f of a. So this would be our final value. This would be our initial value. Now, we can solve for either of these things. So basically, f of b, our final value, which is usually the one we want, is going to equal, well, we just move this over, our initial value plus our integral from a to b of f of x dx. So how do you get from your initial to your final? Well, you add your change. So this ends up getting my change in my initial and final, which is exactly here, right? That's kind of by definition. So your final value equals our initial plus change. Okay? The antiderivative gives me, or the integral gives me the change. And we have to have one of these two values. So we have to be able to find the integral, we have to be able to have the initial, and then we can solve for the final. Now, similarly, you can solve this for your initial. So if we do bring the initial over and the integral back over here, f of a, our initial, equals f of b minus the integral from a to b of f of x dx. Or in other words, our initial equals our final minus our change. It all depends on what you're looking for. Are you looking for f of a or are you looking for f of b? So are you looking for the final? That's just initial plus change. If you're looking for the initial, that's our final minus our change. So that's kind of up to you as to what you want. For the most part, I would really just suggest writing out this equation right here for the problem that you're looking at, and then identifying which one you're looking for. You're looking for the final, you're looking for the initial, and then just solve the equation for those values. So, for example here, we want to find f of 5. We know that f of 1 equals 3. So we're going to look at the integral from 1 to 5 of, well, square root of 4x squared plus 5 dx. You cannot do this antiderivative. It's a lot like factoring. You can distribute, you can find your derivative, no problem, but trying to factor backwards is impossible. So this would give me my change. So if I want to find f of 5, which is my final, I need to add in my initial. So f of 1 plus my change. If you're not following that, remember this thing means the antiderivative, which would be f of 5 minus f of 1. So the antiderivative of here becomes f. You plug in 5 here. Nope. Come on. You plug in 5 here, and then you plug in 1 here, and you solve for the one you're looking for. So in other words, our final, which is f of 5, equals our initial plus our change, the whole shebang over here. So how do we find these numbers? Well, the initial f of 1 is given as 3 plus, how do we get this thing? Well, we seriously just type it in our calculator. So the calculator can do it even if we cannot do it. So we bust out our calculator. And you can do this graphically, or you can just do this on the main screen. Off a window, find our f and int. We want to start at 1 and go to 5, and we just type it in. And enter, and we get 25.865. So our final answer is 28.865. Remember, go 3 decimal places on that. That's interesting that that's stuck there. That's cool. And that's really it. So let's set up one more, and I'll let you knock this one down. So we want to find f of negative 2. So the integral from negative 1 to negative 2. Now the problem with that is this is actually to the right of this number. So if you're not really 100% sure what you're looking at, well, just write out what this is definitely. This is definitely f of negative 2 minus f, capital F because it's the antiderivative, of negative 1. So we're trying to solve for f of negative 2. So we bring this over. And it does not matter that the bounds are backwards. Your calculator will take care of that. As a matter of fact, this graph is going to be a positive thing, but when you type this in the calculator, because you're going to be going from right to left, you'll get a negative out of it. So it doesn't matter if your bounds seem goofy. If they do seem goofy, I would definitely write out the definition here and then just solve for the value you want. So in other words, f of negative 2, once we bring this f of negative 1 over, should be f of negative 1 plus the integral from negative 1 to 2 of e to the x squared. The other option, if you don't like that, is you could always just reverse your bounds. So if we do reverse the bounds and make it to negative 2 to negative 1, f of x, keep it lowercase dx, well, what would that be? That'd be f of negative 1 minus f of negative 2. So if I do bring this over, all of a sudden, I get pretty much the same thing, except there's a negative symbol here. So I'll get a negative f of negative 1. When I divide by negative 1, that'll make it a positive. And then I'll get a negative in front of this integral, but the bounds are switched. And that's true anytime the bounds are switched. So if you don't want to do it in the way that this problem kind of was set up and you want to switch the bounds, that's fine. Just write it out as what it is and you will get the exact same thing. All right, so that's pretty much it. Good luck. There's a bunch of problems. You will probably be done with these before class is over. Oh, I do want to do maybe this last one here real fast. So go to bottom of page 22. Let's see if we can answer this. So our dx dt is that, and our y of t is there. So the position at particle at time equals 3. So some of this is pretty silly. Like at time equals 3, what's the y value? Well, the y is going to be negative 1/2. And this is just y of t. That's just what it is. Okay, so now we have dx dt is here, so we want the x position at 3. So what do we know? We know at t equals 0, we're at 5, only looking at the x. So we want to go from 3 to 5, really. I want to know about 3. I know, sorry, we don't want to go from 3 to 5. We want to go from 0 to 3. We know something about 0. We're trying to find something about 3. Now I'm just going to write dx dt in terms of dt. There's our problem. Our variables are in terms of t. So it really ends up being just the antiderivative of dx, but that's okay. We can't do this, but again, this would be equal to x of 3 minus x of 0. So our goal is to find x of 3, so that's our final. So it should be our initial plus our change equals our final. Our initial is 5 plus, how do we find that thing? Well, we do the antiderivative of that in our calculator to find it. So try to figure it out, and that's what belongs right here. All right, have fun. There's no book homework associated with this, but try to answer all of the rest of these questions as best you can. This side's a little bit easier, pretty much a little bit more straightforward. These are a little bit more conceptual. All good.